In this video, we are going to go over carboxylic acids. Carboxylic acids are a functional group characterized by a carbonyl group, a carbon double bonded to an oxygen, in which the carbonyl carbon, or the carbon bonded to the oxygen, has a bond to a hydroxyl group, an OH group, and a single bond to an R group. The condensed notation, you'll see it as either RCOOH or RCO2H. Carboxylic acids are found throughout nature, and they are also found in many intermediates of metabolism. They play an important role in biology because of their chemical properties as weak acids. So carboxylic acids are weak acids. And their physical properties depend on the pH of their environment, so the environment around them. These are some examples of carboxylic acids. We have methanoic acid. You can see that the ending of each compound is oic acid. We have one carbon carboxylic acid. Its common name is formic acid. We have the carbon double bonded to an oxygen, the carbonyl group, singly bonded to an OH group, and then bonded to an H. Propanoic acid is a 3-carbon carboxylic acid. We have carbon double bonded to oxygen, singly bonded to an OH group, and then R is the rest of the molecule. Benzoic acid, see that the R group is an aromatic ring. Carbon double bonded to oxygen, bonded to an OH group. And then ethanoic acid or acetic acid, that is your common vinegar. And you can see we have a picture of oil and vinegar together. So carboxylic acids versus alcohols. Carboxylic acids and alcohols have different chemical and physical properties. So a carboxylic acid, you can see here, the whole group is the C double bonded to an oxygen plus the OH group. Remember, so phenols are the aromatic ring and the OH group together. Alcohols are just the carbon and the OH group. So all of these have the hydroxyl group attached, but the carbon that the hydroxyl group is attached to is bonded to different things. The carboxylic acid, the carbonyl carbon, so the carbon bonded to the oxygen and the OH act as a group together and will have different properties than an alcohol or a phenol. Carboxylic acids are weak acids, so they donate protons to form conjugate bases. And the conjugate base of a carboxylic acid is called a carboxylate ion. So we have carboxylic acid in water. Water is going to take this proton, and carboxylic acid is going to donate that proton. This makes these electrons within the oxygen-hydrogen bond go back to the oxygen, and they are right here, and it creates a negative charge on the oxygen. And we have this new OH bond on water. That extra bond is now making the oxygen positive. So our conjugate base of the carboxylic acid is this carboxylate ion, which has a one less hydrogen and a negative charge on the oxygen. The carboxylate ion is favored at physiological pH, so the pH of your body. The carboxylate ion is favored. So carboxylic acids form strong hydrogen bonding intermolecular forces due to the strong OH dipole, bond dipole. The carbonyl has a negative, partially negative oxygen, therefore the carboxylate can form dimers. So you can see here, this is one carboxylic acid. You have a partially positive carbon of the carbonyl, partially negative of the carbonyl oxygen, the oxygen bonded to the carbonyl carbon, partially negative oxygen of the hydroxyl group, and the partially positive of the hydrogen bonded to the oxygen of the hydroxyl group. This can bond with another carboxylic acid, forming a dimer. This dimer is bonded through the hydrogen of the hydroxyl group to the double bonded oxygen on both sides. And carboxylic acids can be either liquids or solids at room temperature. The carboxylic acid is neutral, and carboxylate ions are negatively charged ions or anions. Carboxylate ions form ion dipole interactions with water molecules, making them more solid than their acid forms, which have hydrogen bonding. So even though the carboxylic acid has hydrogen bonds and soluble in water, the carboxylate ion is more soluble in water because of the ion dipole interactions. The solubility of carboxylic acids depends on the number of carbon atoms and the number of carboxylic acid groups in the molecule. So as the number of carbon atoms increases, the solubility of carboxylic acids decreases. But as the number of carboxylic acid groups increases, then solubility increases. So fatty acids are carboxylic acids with the R being a long hydrocarbon. Hydrocarbons are just hydrogen and carbon with an even number of carbon atoms. So we have here stearic acid is a fatty acid. We have a carboxylic acid functional group at the very end. And then the R group is the whole rest of the molecule, this long hydrocarbon chain. Soaps are the conjugate bases of fatty acids, so the carboxylic ion. So when this H leaves, you create the carboxylic ion, and when it's in that ionic state, it is a soap. Citric acid is in citrus fruits, and it's a key intermediate in the citric acid cycle, which is an important biochemical pathway involved in energy production. You can see here has 1, 2, 3 carboxylic acid groups in it. Citrate is the carboxylate ion form, and you can see that all of the carboxylic acid functional groups lost their hydrogen or in their ionic form. Pharmaceutical compounds containing carboxylic acids are prepared in either the molecular or neutral state or the carboxylate ion form. Ibuprofen or Motrin and Advil have the carboxylic acid form. Naproxen or Aleve is the carboxylate ion form. And with the negative ion, we also have a positive ion to go with it, and a lot of the times it's sodium. So in summary, carboxylic acids contain a carbonyl group where the carbon center has a bond to an OH group and an R group. The condensed notation for carboxylic acids is RCO2H or RCOOH. In a skeletal line structure, both oxygen atoms and the hydrogen bonded to the oxygen must be drawn. Carboxylic acids are weak acids. In water, carboxylic acids undergo a reversible reaction to form hydronium ions and the carboxylate ion. At physiological pH, equilibrium favors the carboxylate ion form of the carboxylic acid. Carboxylic acids form strong hydrogen bonds as dimers due to that partial negative charge on both oxygens and the partial positive charge on the OH hydrogen. Carboxylate ions are also much more soluble in water than the neutral carboxylic acids because they are ions and therefore form the ion dipole interactions. And then fatty acids have a long hydrocarbon chain with a carboxylic acid at one end. Soaps are the conjugate base of a fatty acid.